Hunter Kanoki, and this is Fool's FAQ, a show where I take the internet's most burning questions and give you an answer that'll make you the smartest person at your next stargazing party. On today's episode, Mother Nature's clickbait. Have you ever actually stopped to think about why the sky is blue? I mean, really think about it? I mean, it's such a fundamental part of our daily experience that we barely even question it. But when you stop to think about it, it's kind of wild. The sky is blue, just constantly blue, no other explanation. But if you're like most people, you probably learned at some point that the ocean is blue and the sky reflects the ocean, so boom, blue sky, right? Well, wrong. And I'm willing to bet you've never actually verified that assumption. Here's the thing. That explanation sounds reasonable. It feels intuitive, but it's one of those persistent myths that just won't die. And the real answer? It's actually way cooler than a simple reflection. The truth involves physics, light waves, and something called Rayleigh scattering. So, stick around because by the end of this episode, you're going to understand exactly why our sky is blue, and more importantly, why it's not purple. So, let's start with what's actually going on up there. When sunlight travels from the sun to Earth, it's what we call white light. But here's the thing. White light isn't actually white in the way you might think. It's not just one pure color. It's actually a combination of all the colors of the visible light spectrum mixed together. Red, orange, yellow, green, blue, indigo, and violet. Think of it like a pack of crayons where all the colors are blended into one. When all those colors hit your eye at once, your brain perceives it as white. But the moment that white light enters the Earth's atmosphere, things get interesting. The atmosphere is packed with tiny molecules, mostly nitrogen and oxygen. These molecules are incredibly small, much smaller than the wavelengths of visible light. And when light waves encounter these molecules, something called Rayleigh scattering happens. Now, scattering is exactly what it sounds like. The light bounces off these molecules and gets sent off into random directions rather than continuing straight ahead. Here's where wavelength becomes important. Different colors of light at different wavelengths. Red and orange have relatively long wavelengths, while blue and violet light have much shorter wavelengths. And here's the key. The shorter the wavelength, the more likely it is to scatter. This isn't just a little bit more. Blue light scatters roughly 10 times more than red light. That's a massive difference. So when white sunlight comes through the atmosphere, the blue light is getting bounced around in all directions, while the red light mostly passes right through. Because blue light is scattering in every direction, it's coming at you from all parts of the sky, no matter where you look up. To your left, to your right, straight ahead, there's blue light reaching your eyes from that direction. And that's why the entire sky appears blue. It's not the blue light going directly from the sun to your eyes, it's the blue light that got bounced around by those nitrogen and oxygen molecules and happened to end up pointing downward towards you. Now, you might be wondering, well, if violet light has an even shorter wavelength than blue, shouldn't the sky be violet instead? Well, that's a great question, and honestly, it should be, theoretically. But there are two reasons why it isn't, and they're both fascinating. First, our eyes. The human eye has 3 types of color receptors called cone cells, and they don't all have the same sensitivity. We're actually way more sensitive to blue light than we are to violet light. In fact, our eyes are kind of terrible at detecting violet. So, even though there's more violet light being scattered up there than the blue light, we can't see it all that well. It's almost like our eyes are calibrated to see blue better, so that's what dominates our perception. Second, a lot of that violet light is absorbed by the upper atmosphere before it even gets a chance to reach us. The sun actually does emit violet and even ultraviolet light, but much of that never makes it all the way down to our eyes. It gets absorbed by ozone and other gases up there, so between our eyes not being great at detecting violet and the atmosphere absorbing a good chunk of it anyway, blue is what we see. But wait, there's even more to this. Have you ever noticed that the sun itself looks different colors at different times of day? During the day, when the sun is high in the sky, it looks whitish yellow. But at sunrise and sunset, it turns this deep orange or red. This is Rayleigh scattering at work, but in reverse. Here's what happens. When the sun is low on the horizon, the light has to travel through a much thicker layer of atmosphere to reach you. The light is coming in at an angle instead of straight down. Because it's traveling through more atmosphere, all that blue light that normally scatters gets scattered away completely. It's being bounced off in different directions. But the red and orange light, with its longer wavelengths, isn't scattered nearly as much, so it continues on its path straight to your eyes. That's why sunsets are red and orange. The blue light literally got knocked out of the beam before it reached you. And here's something wild. Leonardo da Vinci actually figured out part of this back in the 1500s. He watched sunlight passing through wood smoke and noticed that it turned blue. He was basically observing Rayleigh scattering without having a name for it or understanding the physics. This phenomenon was properly explained in 1871 by an English physicist named John William Strutt, though everyone knew him as Lord Rayleigh. He mathematically described how light scatters off molecules in the atmosphere, and he figured out that shorter wavelengths scatter way more than longer ones. So, the whole scientific principle is named after him, Rayleigh scattering. But here's another mind-bending part of this. If there were no atmosphere at all, the sky wouldn't be blue. It would be black. That's why if you go to the moon, which has virtually no atmosphere, the sky is completely black, even in the daytime. The sun is visible, but the sky around it is black as night. There's no atmosphere to scatter light in all directions, so you don't get that diffuse blue glow we're used to. Same thing in space, black. The blue sky is actually a gift from Earth's atmosphere. This same principle explains why the sky on Mars looks different. Mars has a very thin atmosphere, and it contains a lot of fine dust particles. Instead of scattering blue light more efficiently like Earth's atmosphere does, those dust particles tend to scatter red light more. So, when you see images from Mars rovers, the sky often looks reddish or peachy, completely opposite of what we see here on Earth. It's the same physics, just different particles doing the scattering. So, let's bring this all home. The sky is blue because sunlight is white light containing all colors. When that light enters Earth's atmosphere, it interacts with tiny nitrogen and oxygen molecules, and then blue light, with its short wavelengths, scatters off those molecules way more efficiently than red light does. That scattered blue light reaches your eyes from every direction in the sky, so the whole sky looks blue. Our eyes are also just really good at detecting blue and not so great at detecting violet, even though there's more violet being scattered. When the sun is on the horizon at sunset, the light travels through a thicker layer of atmosphere, scattering away the blue completely and leaving the red and the orange. It's not a reflection of the ocean, it's not magic, it's just physics. It's Rayleigh scattering, and now your fun fact arsenal just got an upgrade, and now you know exactly why the sky is really blue. Thank you so much for listening to Fool's FAQ. Feel free to leave a 5-star rating wherever you get your podcasts, as it also helps new listeners discover the show. For more fascinating answers to your burning questions, subscribe wherever you get your podcasts, and always stay curious.